I am in a new window and titled it Organ 61 Key Organ Keyboard. Oh, actually, that's redundant. 61 key. 61 electronic organ 61 key. Okay, that's keyboard. Key on, off. Okay, and so I guess the next thing we could do is import. No, that's not what I want to do. What's this? No. Double tap. Photos or videos, camera, scan, link, insert from. Okay. So, photos or videos. Let's go here. Let's go import a photo of the Farfisa, a photo of the keyboard, a photo of the frequency, and let's see. Not now. Okay, so we have a photo of a Farfisa synthesizer. I have my own organ setup at home, and we're going to increase the size of the aspect ratio, and then let's see if we can move this forward. Move forward. Front. Okay. Okay. So, if we're going to reread this section over here, so that's our Farfisa organ. I'm going to place this one in front just because we want to be able to determine how these frequencies work. And then while this screen is open in freeform, I'm going to go onto Safari. Oh, I was doing to understand how refrigerator works. We're going to go onto Google and then search for what am I searching for? Let's see my web browser. Farfisa organ. Let's see, oscillator for Farfisa organ. Organ chip, IC chip, and then I think it's a a D flip-flop. That makes it a divider. Frequency divider. Farfisa organs, specifically the compact series, made between 1964 and 1970, traditionally used 12 independent discrete transistor-based LC oscillators to generate the top octave of notes. These high-frequency square wave signals were then fed into a series of transistor-based flip-flop frequency dividers to produce lower octaves. This video provides a technical overview of a Farfisa organ, including its oscillators and dividers, and I'll do my best to explain. So there's a video here. I would very much enjoy viewing the video later on. However, there's some text here from Gemini, the artificial intelligence engine. And it says here, between the oscillator system, the frequency divider system, flip-flops, later IC systems, IC-based systems, and key component for repairing and cloning. So it says, within the design, each of the 12 notes from C to B, remember C is to the left of the two black keys, and a B is to the right of the three black keys. So, and then C and B are right next to each other. There's no, C sharp is B, or C flat is B, and B sharp is C. And remember that each octave is repeated, and in the 61 key there are 5 octaves, right? The oscillator, each of the 12 notes C to B has its own oscillator board producing the highest octave. Components, the oscillator relies on a tunable inductor and transistors to create a sharp square wave. Okay, so that tells us something. We are using a square wave in many modern synthesizers. We have sawtooth waves, we have square waves, we have triangle waves, we have sine waves, and we have various waveforms that are the summation of multiple sine waves, which is called Fourier transform or Fourier series. And this gives us some important information. We know that we need a square wave oscillator, and it says here the pitch is adjusted by turning a ferrite slug in tuning coil. Okay, so later on I'm going to search up a square wave oscillator. But say we use a square wave oscillator as like a clock signal for each key that's pressed, and there are 12 notes here, C to B, 12 notes, and there are 5 octaves. 5 times 12, that's 60, and plus the 1 repeat of the C note on the highest right side. And then if we go back to the Freeform app, remember that if I use the pen tool right now, I'm going to use a blue, actually I'll use a green ink. And if I move that away, this is the lowest C, this is the highest C, this is probably C minus 3 or C minus 4, this is probably C3 or C4. When it goes to pitch and frequency, however, this is the lowest. I wish I could type instead. Let's see if I could type the text in. Oh, okay. Oh, I see. The text is over here, and the text is over here. And then I'm going to delete that. Double tap to enter text, and then here I'm going to say low frequency or low fric. And this is similar to the term on many synthesizers, LFO, which stands for low frequency. Frequency oscillator, which sort of acts like an LFO, sort of acts like a whammy bar or a tremolo, a vibrato. Think vibrato, or tremolo in musical terms. And then over here we have the highest frequency or high frequency. If we were to use filters, we would have like a high pass filter or HPF. High pass filter, low pass filter, band pass filter, band stop filter, etc., etc. That's for some other time, though. We'll assume that using a square wave oscillator goes like this, right? Obviously, if I use the square like this, then square wave would be naturally a repeat of this. How do I copy this? Like duplicate? Right? Okay. And if I use a line over here, okay. How do I change the color? How do I change the color of this? Okay. Yeah. Geometry. Okay, that's kind of aside from the point, but let's go back. But a square wave, I'm going to use the pen tool because I'm going to highlight the square wave in blue, however, so we have a signal that goes like this, signal that goes like this, and this is voltage over, guess what the horizontal dimension is? It's going to be lowercase t, time. And keep in mind that a square wave, if you've ever been curious about electronics or mathematics, differential equations, which is one course after Calc 1 through 3, then if I have a sine wave, and if I take a sine wave that is just, oops, didn't mean to, okay, so sine wave that is half that frequency, and if I again add those together, and if I go with a sine wave that is once again half, okay, maybe not like that, but let's just say that it's twice the frequency of this, right? So then these are a summation of sine waves. The more as you sum these, and remember sum in mathematics is sigma, n equals 0, or n starts at 1, and then this k equals n number of times. Let's just say that it's where k is equal from 0, 1, 2, 3, dot, 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 oops, dot, dot, dot. This is where all the algebra that you learned, all the trigonometry that you learned, all of the pre-cal, the calculus, this isn't saying that I'm going out there and telling you that your English class doesn't matter. I'm not telling you that your history class doesn't matter. All of those things are important, but if you want to go as far as you can in math, then this is where learning about sigma or learning about integrals, sigma is the digital form of the integral, or the double integral, or the triple integral, and here is a closed loop integral. You know, so you have all this in a dt, or all that in a dt, or dx, or dy, etc., or dz, excuse me, dz, because that's all in 3 dimensions, right? 1d, 2d, 3d. And all this is all in 3-dimensional space. So, you know, it gets a little bit more complex with electromagnetic waves, but let's just say that when we press a key, we press the 440 hertz, 440 hertz, that's your frequency, right? And then likewise, here is, what's this? 220. And then what's this? This is 880. And then if we double that again, 800 plus 800 is 1600. 1600 plus 80 times 2. What's 80 times 2? 160. 1600, 160, 1720, right? 1720 is the next frequency up, hertz. And I hope that explains how some of that works. I'm doing my best to explain to myself how this works. But this is a square wave. Oops. SQ square wave.